me introduce today's speaker, Krzysztof Jachymski, who will be talking about dynamics of charge impurity immersed in a Bose-Einstein condensate. Krzysztof is graduated from our department. He was a PhD student of Zbyszek Jaszek, and then he spent a few years as a postdoc in Hans-Peter Büchler group and Tommaso Calarco, and now he's back in our department, starting a career at Faculty of Physics. So, Krzysztof, please.
Yeah, thank you.
Yeah.
And hello, everyone. So I've been in Warsaw for quite some time now, like a few months, but I had only a few chances to interact with you, which is a very regrettable thing, but it's still some kind of pleasure to speak to you remotely about our results. And the work I will be presenting today concerns a very specific experimental system, and the experiment has been conducted in Stuttgart in the group of Tillmann-Pfau, but the leading PhD student was Thomas Dieterle, and the actual leader of the subgroup is Florian Meinert. And the system I would like to consider is an charged atom of rubidium immersed in its parent gas of rubidium bosons in a quantum degenerate state. But the field of quantum impurities is really a very diverse and widely studied field. And even at the classical level, it's very interesting. And here the history reaches, for example, to the Brownian motion of particles inside the fluid. And it inspired the development of kinetic theory, which was one of the foundations of modern microscopic physics. And if we consider a motion of a classical impurity in a dense medium consisting of many other particles, we can see that between successful collisions with the medium particles, the motion of the impurity should be ballistic, meaning that its mean displacement should grow quadratically with time. But as a result of very frequent collisions, which randomize the direction of the particle, the motion instead becomes diffusive, and the area explored by the impurity grows with time only linearly with a characteristic constant. So these are the two extreme situations, but there are also many others, and this can be translated to the quantum picture if we think about spreading of a wave packet, which is initially put in some position and is moving in a potential consisting of many impurities. So a ballistic spreading would mean a quadratic type of spreading, whereas diffusion would be a linear spreading of the wave packet. But if the resulting potential is disordered, for example, we can also observe other types of motions, such as subdiffusive motion or complete localization of the wave packet. And also in a classical picture, we can see diversions from diffusive or ballistic motion, for example, due to memory effects or just the simple inertia of the fluid. So if the particle strongly interacts with the medium particles, it can drag along some of them. And as a result, we will see an effective motion of a particle which will have a very different effective mass instead of the bare mass of the impurity. And this can be also directly related to the question of conductivity in materials. For example, if we consider motion in electric field of a charged particle, such as an electron inside the material, due to frequent collisions with the impurities or just with the atoms, we can see that the particle, instead of constantly accelerating, it will finally reach a steady state in which its motion is again diffusive, and it depends on the magnitude of the electric field, but also on the characteristic time, which we can relate to the time between the average time between collisions. And the resulting current density is, of course, proportional to this charge particle velocity and the density of electrons. And we can connect it with the conductivity, sigma, which is then related to the mobility. And the mobility in this simple classical picture is just directly proportional to tau.
May I have
And
a
this,
question?
yes?
Because in the title is impurities in quantum media, then is quantum impurity in a medium. And what is quantum about these examples here?
So far, nothing is quantum. So this kinetic theory of zero conductivity is an electron, which is a classical particle undergoing collisions.
Okay.
So even in a classical theory, we can observe the increase of the effective mass, but this will be most interesting in the quantum picture when we try to quantize both the electron motion and also the medium. And we can think, for example, again, of an electron problem interacting with the crystal and seeing the lattice phonons, so seeing the excitations of the medium now. And here, this is, of course, an extremely old problem. And it inspired the scientists such as Landau and Friedrich to introduce the concept of a quasi-particle called the polaron, in which now the electron is dressed with the excitations of the medium. And as a result, if we study the properties of this quasi-particle, we will see, hopefully, if we can calculate anything, the increase of the effective mass. And the notion of polarons, so electrons in a crystal, turned out to be extremely important in understanding certain types of superconductors. So there are models in which, due to creation of bipolarons, we can see indication of pairing in the system, but not of bare electrons instead of polarons. And this, due to a change in the effective mass, these bipolarons can have very low effective mass, which translates to a very high condensation temperature, and we land at a high TC superconductivity in certain types of models. Of course, this is not the only one possible. And one particular application of ultracold gases is to test these kinds of theories by creating a very well-controlled impurity and a very clean medium at quantum degeneracy, and then observing the properties of these impurities. And here we have a lot of possibilities. We can change the medium from a bosonic gas to a Fermi degenerate gas. We can control the coupling to the medium by means of Feuerbach resonances. And we have excellent measurement schemes to not only detect the static properties, such as the energy of the polaron, but also to study its non-equilibrium dynamics. And here, actually, last week we had a speaker at the seminar, Jan Arlt, who has a very successful experiment studying Bose polarons with one of the first observations of the properties. But of course, you don't have to study a Bose-Einstein condensate to do these kinds of physics. So the first experiments with impurities in sort of quantum media were conducted with superfluid helium, which is also intrinsically quantum. And by immersing ions in superfluid helium droplets, it was suggested that these particles have extremely low mobility, much lower than expected from classical theories, which might be associated with an increase in the effective mass. And these experiments inspired Gross to propose a mean field-based ansatz for the wave function of the system, in which the ion moves like a plane wave, but the medium is described by a mean field ansatz, where this F function describes the correlation between the ion and the gas. And this is all done in the picture co-moving with the ion. And this kind of ansatz is enough to actually, after some additional assumptions about the strength of interactions and their character, to calculate the increase in effective mass, which is which turns out to be huge because the ion drags thousands of particles with it during the motion, even though the medium is superfluid, so there should be no such phenomenon. But due to the large strength of the interactions, this effective particle is very large. So we would like to study a similar kinds of systems and a charged particle but now in a Bose-Einstein condensate, because then the theory of the medium is a bit simpler than for superfluid helium. So at very cold temperatures, if we had a neutral impurity, it would interact with the medium by van der Waals potential, which usually has a range of about 100 Bohr radii, which is much lower than any other length scale in the system. So in a dilute cold gas, the Broglie wavelength is large, and the gas is extremely dilute, so the particles are far away from each other, and this 100 Bohr radii is extremely small. So as a result, we can forget about the details of the interaction and instead introduce a pseudo-potential, which just has a zero range, and is described by a single parameter, the scattering length, coming from the S-wave phase shift in a single collision. And the cross section in this case for a collision is isotropic and proportional to the square of the scattering length. So the description of Bose polarons is not simple, but it's simplified by the fact that we can describe all the interactions by a single parameter and then write a comparatively simple field theory where the interactions are taken care of in this effective way. In turn, if we have an ion in a condensate, the interaction now has a slightly different character with a different power law, and it comes from the polarization of the atom by the charge. And now the typical length scale of this potential is an order of magnitude larger. And this means that the interaction length scale interferes with other quantities such as the coherence length of the BEC, interparticle distance. So if we take rubidium gas with a small gas parameter, like 10 to the minus 6, we can immediately check that the interparticle distance in the BEC is comparable with the interaction range. And a further effect, which is important for ions, is that we can, if we see the centrifugal barrier, which describes the higher partial, which is present for higher partial wave collisions, the height of this barrier is given roughly by this characteristic quantity, which for neutral atoms is in a millikelvin range, but for ions, it's sub-microkelvin. And it means that we need to be much colder to safely assume that we have S-wave collisions between ions and atoms. But in a typical experimental situation, it's not possible to cool the system down to below microkelvin energies, in contrast to atoms, but I will speak about this a bit later. And we are dealing with multiple partial waves. So the interaction cannot be safely replaced by a pseudopotential unless we make this pseudopotential complicated and include higher partial wave corrections and finite energy corrections. But then we lose the point of introducing a pseudopotential because it's no longer simple. And experimentally, it's very important that a charged particle directly couples to the electric field. So we can really drag it with electric field through the system and make direct connections to the conductivity or similar effects. But it's also a problem because an ion is extremely prone to stray fields, which are necessarily present in all experiments. So typically, if we create an ion, it will immediately escape our system just in a random direction, basically because of the electric field noise. So one needs to control these electric fields very precisely. And so what are the typical experimental systems to study hybrid ion atom platforms? Well, cold ions are typically stored in Paul or Penning traps, which based on time-dependent electric fields. So it's hard to trap a charged particle using electric field because its divergence is 0. So one cannot create a static potential for a charge. Instead, we have to alternate the electric field periodically and create an effective average potential which keeps the ion in place. And this method is kind of nice because it doesn't depend on the species. We can trap any kind of ion in a pole trap as long as we know its mass and we can calibrate it. But this is not a hard job. So one can imagine trapping different species, even molecular ions in pole traps for long times because these electric fields are strong and one can keep the ions there for minutes or even longer. And this is great for applications such as chemistry, in which we would like to study some more complicated reactions involving molecular ions. And then during the reaction, we can usually directly observe it in time by fluorescence imaging if one of these constituents absorbs light. We do not worry about the temperature because the traps are typically quite deep, so a few Kelvins deep. But for our purposes, if we want to see quantum effects, there is a problem of intrinsic micromotion coming from the time-dependent electric fields, which constantly drives the ion and limits its achievable kinetic energy. Even if we laser cool it and then sympathetically cool it in a cold gas, this micromotion will still keep it at finite kinetic energy, which typically is far above the S-wave limit. So there is a need for other trapping technologies. And one idea is that we can use, in principle, an optical trap. So ion doesn't differ too much from neutral atoms, especially if it's an alkaline earth ion. It has one valence electron. It couples greatly to lasers. So we can construct an optical trap for ion just as for atoms. And this idea is pursued in the group of Tobias Schetz in Freiburg. But these traps are quite shallow compared to pole traps. And if we have any kind of a stray electric field, this field will be stronger than the trap, will eject the ion from the trap, and the system will not be useful. So one needs to have an incredible level of control, and this has only been achieved so far in this one laboratory. So another idea, which is sort of intriguing, is to use a charge to trap another charge. And well, this is commonly done in atoms. So a hydrogen atom can be thought of as a trap for the ionic core or as a trap for the electron, which is just bound and doesn't escape. And this way of thinking is, for example, common in the group of Tillman-Pfau, where they create giant Rydberg states inside cold gases, and then they can study the physics of either the electron, of the ionic, or the ionic core. But both of them are present in the system at the same time. So if you want to study the ionic core, the best idea is to excite the Rydberg atom to very high levels so that its size exceeds the size of the condensate itself, and it has been done. It's actually not so hard. It only requires a relatively small condensate and excitation numbers of the order of 100. And then we can hope to see some effect of the ionic core present in the gas. And the first indications that the ion is present and affects the system in some way was the line shift of the excitation, of the Rydberg excitation, and then a blockade of the Rydberg excitation induced by the interaction of the ion with the gas atoms. So if we try to excite a Rydberg atom, but there is a comparatively strongly interacting ion present, it shifts the excitation frequency a little bit. And so we lose the signal if we are at resonance with the transition in absence of the ion. So this kind of excitation blockade is a way to detect the position of the ion in the gas, and it has been demonstrated in this paper. But the current experiment is a step further, and we now have a free ion without an electron moving in a gas, and the ion is created by first exciting a Rydberg atom and then an ionization field. So here's the experimental scheme that I would like to discuss. First, we create a high-N Rydberg excitation in the BEC, but its frequency of the laser is chosen such that the atom is preferentially created in the low density regime. So not directly inside the BEC, but somewhere on the fringe. And then it's ionized by a very short electric field pulse. So the ion starts moving quite quickly, and we need a stopping pulse to compensate this. So it's ionized, but it more or less stays in place. And then a very tiny electric field is applied such that it moves towards the dense regions of the BEC at constant electric field for some interaction time. And then after this interaction time, a very strong electric field pulse drives it towards the detector, which is a microchannel plate. So an effective detector for charges. And after some time of flight, this charged particle arrives at the detector, and it's possible to distinguish the types of products that arrive, so that the mass. And here you can see the Bohr experimental results, in which the time of arrival, so the time of flight of the ion after the extraction from the gas, is recorded as a function of the interaction time within the BEC. And the blue case is the motion of the ion through a BEC, while in the red case, the temperature of the gas is much higher, so that it's also less dense, and the ion probably doesn't meet so many atoms during the interaction. And you can see these cases differ. So if we let the atom interact with the gas for long enough, the time of arrival will be profoundly different. And this is an indication that if the ion travels through a dense gas, it actually undergoes some change in its dynamics due to the interaction with the gas atoms. So in the kinetic picture, it will just undergo several collisions, and this will affect the arrival time at the detector. But now we need to understand this signal a little bit better. And we do it by a semi-classical simulation, numerical simulation, in which the ion is treated as a free particle moving in electric field from collision to collision. And the collision, so at each time step, there is a certain probability for it to meet an atom from the BEC and collide with it. And we just repeat this many times in a Monte Carlo fashion to get an average result. If a collision happens, it does so with the rate dependent on the gas density and on the interaction strength. And we can compute the full cross-section for this collision. It's not a problem numerically. Get the scattering amplitude and then draw a scattering angle from the appropriate probability distribution. So after the collision, the ion gets deflected somewhere and keeps traveling through the gas ballistically until the next collision. And the electric field increases its energy. And then at some point, the ion will escape the condensate. There will be no more ions, so then it will just move freely. And then from this kind of data, we are able to extract the drift velocity of the ion in a gas. And then it's also its mobility, which is just the derivative of the drift velocity with respect to the electric field. And this effect is transient because we have a finite size BEC. So this drift velocity is more or less constant, but only for a short period of time before the density drops and then the ion accelerates. So this drift velocity data and the mobility we can extract both from the simulation and from the experiment itself. And here are some results. So this is the measured in the top panel and simulated in the bottom panel ion arrival time as a function of the interaction time with the BEC. And there are two different electric field values. So here the black points are the averaged like center of mass of these histograms at many trajectories, and the red points correspond to a ballistic motion without any collisions with the atoms. I mean, with rare collisions with the atoms. And you can see the experimental data is pretty well reproduced with, of course, a little bit less noise because we don't capture the density profile of the condensate and the stray field profile perfectly. But we can now plot the drift velocity in both cases as a function of an electric field. So after analyzing many of these histograms, we come up with these two lines showing that the velocity depends linearly on the electric field. And this is very important because it means that the mobility is actually a well-defined notion. And another observation is that these two fitted lines do not coincide exactly. So our simulation points out to a slightly lower mobility values. So if you put it in physical units, we land at the experimental mobility being 47,000 centimeters square per volt second. And the simulation result is within the error bars, but on the verge. So there is some systematic deviation. And it can be either explained by a little larger stray fields, which increase the ion mobility a little bit by putting it subject to more noise, or by inelastic processes, which we do not include in the simulation at all. But for us, the most important thing is that actually this ion undergoes diffusive motion. So because we can really fit a straight line to the experimental data, maybe there are not so many points here, but it means that the ion really undergoes frequent collisions and it's in the regime of diffusive motion. It's not a ballistic type of motion. So we have a free particle diffusing in a quantum medium. But the inelastic processes are also interesting on their own. And we have evidence that they happen in the gas because sometimes a rubidium-2 plus ion, so a molecular ion, is detected instead of an atom at the detector. And this can only be a result of a three-body recombination in which the ion interacts with two rubidium atoms at the same time and creates a weakly bound molecule. So this process should depend on the square of the density of the gas. And we don't know so much about it, except it's probably a weakly bound state, this rubidium-2 plus. But the only studies are based on classical trajectory calculations. And then what's probably even more interesting is that this molecular ion also stays in the gas. It has, of course, higher energy because this binding energy has been released, but it still undergoes secondary collisions with the gas atoms, and we also have evidence for that. So here on this complicated figure, you can see the signal of the molecular products and atomic products as a function of the interaction time with the condensate. And here the electric field is kept as low as possible. We don't want transport, we just want to study the inelastic collision dynamics. So the total signal is more or less constant, but the longer we keep the ion inside the condensate, the more molecules we observe. But the experiment now can be made a little step and vary the strength of the excitation field at the end. When we try to extract the ion from the gas, we can do it with a strong pulse or with a weak pulse. And the weak electric field pulse will just push it gently towards the detector, but a very strong pulse will also dissociate the molecule. And as a function of the strength of this field, we can see that the fraction of the detected molecules changes. Especially at long times, this time dependence is more profound. So it's a little bit of a measure of the binding energy of the state that we have when we try to extract the molecule. And if we make a classical or semi-classical model of this dissociation of a molecule due to electric field, based just on over the barrier ionization, dissociation, we can link this field strength of this dissociating field strength to the binding energy of the molecule. So this figure is just a translation of this figure to the language of binding energy. And we can fit a theoretical model based more or less on the same Monte Carlo calculations as before, but with additional inelastic collision processes, changing the vibrational state of the molecule. And we see a fairly good agreement, especially at long times, because at short times, we are not exactly sure what kind of initial state we have in the system. So there is a little bit of a mismatch with our crude model, but at long times, this doesn't depend on the initial state so much. This distribution becomes more universal. Here you can see the histogram showing the population of different vibrational bound states at short times. So the mostly occupied states are in this 6 to 10 region, which is, and I'm counting from the dissociation threshold down. So this state is the most weakly bound state available. And at long times, due to frequent collisions with the gas, which are inelastic now and change the vibrational state, this distribution moves towards more strongly bound particles. And this is also evident here. So we have a comparatively simple model for this vibrationally inelastic collision. It's in principle a three-body problem, which makes calculations a bit complex. But for an atom-molecule collision, we can make it very simple. So I will use Jacobi coordinates, in which the small r is the internal coordinate of the ion or of the molecule, and the big R is the center of mass of the molecule distance between the center of mass of the molecule and the atom. And we know that initially we have a molecule in a well-defined vibrational state, and at the end we also are interested only in molecules with some other vibrational states. So we can decompose the interaction potential into these channels, molecular channel states, and the interaction becomes a matrix coupling different channels. So these coupling elements are the crucial thing here, and they are shown in these little figures. And what we can see is that this effective interaction between the atom and molecule, it has to behave in the same way as the ion-atom interaction. So still the leading term is the polarization potential. It can depend at short range on the vibrational state that we consider, but the asymptotics is always the same. And the coupling elements here between a relatively strongly bound state and some lower lying states, and here between a weakly bound state and lower lying states, they also have the same 1/r⁴ dependence, with some possible deviations, again, for very weakly bound states, because they are spatially very extended and we cannot treat them as point-like particles with a charge anymore. But what's evident is that there is the same asymptotics, and that these couplings are relatively weak compared to the diagonal elements. These are orders of magnitude smaller in each case. So we can also safely use some approximate methods, such as Born approximation. In this case, it's a distorted wave Born approximation, to calculate the state-to-state collision rates. And this simple model was the basis of the figure I showed on the previous slide, in which this redistribution of the vibrational population has been shown. So this is the only ingredient that we need to extend our simple semi-classical model. Now, what would happen if we really reach the quantum regime? Because here again, one could argue it's a charged particle in a gas, but all the results are perfectly well explained by a classical model in which there is a collision, individual collisions with the gas atoms. So it's again this kinetic theory of Drude from the beginning of the century, and we are not doing anything really impressive from the theoretical point of view. So if instead the the temperature was lower, which is just a technical difficulty in our case. So it's about controlling the electric field noise again. Then we would interact with the condensate excitations instead of individual particles. So we would move to the spectrum, which is more phonon-like, and this would be the part that's more interesting. And then the particle would create an analog of a polaron with an increased effective mass. And we could detect it probably quite easily just by measuring the mobility in the same way as we are doing now. Another effect, which would be nice to observe, would be scattering resonances. If we are in the regime of individual partial waves, there could be an atom-ion resonance, either a shape or a Feshbach resonance, which would modify the cross-section very strongly at certain energy. And this would result in profoundly different behavior of the transport, which would be a little bit harder to measure because the ion energy in our experiment increases with time. So there would be only a short period in which this resonance is matched, but still this is a possibility. And finally, there is a prediction that at really low temperatures, another effect emerges, which is the direct hopping of the electron between the ion and the atom, which is possible because this is an ion immersed in its parent gas. So in a collision of rubidium plus with a rubidium, we cannot distinguish the product states. So there is a resonant charge exchange process between the two. And the hopping of electron could increase the conductivity and the mobility of the ion significantly, but only at even lower temperatures. So this is an outlook for the experiment, which hopefully we will reach sooner than later. And now I'm already at my conclusions, which probably leaves a lot of time for discussions. So I argued that ion atom systems, after a few years, are finally approaching the really quantum regime in which single partial waves start to matter, and we see frequent collisions with the gas atoms instead of just chemistry. And I showed you the observation of diffusive ion transport in the gas without any trapping potential for the ion, which enables measurements of transport properties. And a bit of indication that there is also cold chemistry happening in the system, and the weakly bound molecular ions undergo collisions as well, and we can observe them. So this presents exciting prospects for the future. And about the polaron-like physics and effective mass, I will be actually speaking next week on a condensed matter physics seminar, because we have a paper on that as well. And this polaron turns out to have very different properties than standard Bose polarons. And here are the papers on which the talk is based. So I would like to end with an artist's view of the system considered, and thank you for your attention.